Good morning everyone. I am Garima from BSc Chemistry Honors second year. Today we are going to start our chapter Acid and Bases from Pardeep's Inorganic Chemistry Volume 2. Acid and bases 7.1 Arrhenius concept of acid and bases. Arrhenius, a Swedish chemist, was the first to define acid and base in aqueous solution. According to Arrhenius, an acid is defined as the substance which contain hydrogen and which when dissolved in water give hydrogen ion, that is H positive. Accordingly, all mineral acid like HCl, HNO3, H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ion H positive, as HCl in water give H positive plus Cl negative, HNO3 in water give H positive plus NO3 negative, H2SO4 in water give 2H positive plus SO4 2 negative. Arrhenius named this acid which dissociate completely. These There are other acid like acetic acid, carbonic acid and phosphoric acid which when dissolved in water do not dissociate completely into ion. As a result equilibrium is set up between ions and undissociated acid molecule as shown below. Arrhenius named his acid as weak acids. According to Arrhenius, a base is a substance which contain hydroxyl group and which when dissociate in ion give hydroxyl ion OH negative. Thus, substance like NaOH and KOH which when dissolved in water dissociate completely to give hydroxyl ion OH negative, as NaOH in water give Na positive OH negative. KOH in water give K positive plus OH negative. Arrhenius named this base which dissociate completely in water as strong base. There are substances which do not completely dissociate into hydroxide ion. Arrhenius named these substances as weak bases. For example, substance like NH4OH, MgOH twice, AlOH thrice do not dissociate completely to give OH negative ion and can be written as AlOH3 in water give Al3 positive plus 3 OH negative. Hydrogen ions do not obtained from the acid and hydroxyl ion obtained from the bases combine together to form unionized water. Arrhenius described this combination of H positive and OH negative as neutralization reaction. NaOH will give Na positive plus OH negative, HCl will give H positive plus Cl negative. Combining right hand side of 7.1 and 7.2, Na positive plus OH negative plus H positive plus Cl negative will give Na positive plus Cl negative plus H2O. Cancelling the common effect on both sides, we will get H positive plus OH negative will give H2O neutralization. Arrhenius concept is simple and to apply and explain a number of phenomena like neutralization, hydrolysis of salt, strength of acid and bases. However, there are certain limitations which can be described below. Arrhenius' concept of acid and bases is applicable only in aqueous solution. This concept failed to explain the acid or base behavior of substance in non-aqueous medium such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Arrhenius' concept failed to explain the acidic character of substance CO2, SO2, SO3 and basic character of substance like NH3, Na2CO3, CaO, etc. Arrhenius' concept also failed to explain the reaction between acid and base in the absence of water. Although Arrhenius' concept of acid and base suffers from a number of limitations, yet it very useful and informative for elementary approach. Bronsted-Lowry concept. Arrhenius' concept of acid and base was further improved by Bronsted and Lowry. Both these in 1923 incidentally introduced the same definition for acid and base. According to Bronsted-Lowry concept, an acid is a substance which can denote proton, whereas base is a substance which can accept proton. In other words, acid is the proton donor, whereas base is proton acceptor. As a result, Lowry Base concept is sometimes called proton donor acceptor concept. It is represented as acid 1 will give H positive plus base 1, base 2 plus H positive will give acid 2. According to Bronsted-Lowry, a neutralization reaction involves the release of proton by acid and acceptance of that proton by a base. For example, the reaction between HCl and H3 to form the salt ammonium chloride can be represented as the curved arrow shows how electrons must rearrange to result in the transfer of hydrogen atom from the base acid to the base. The unshared pair of electron or nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of structure of reactant and product shows that the hydrogen atom which was bonded to chlorine in the reactant is bonded to nitrogen in the product. Thus a proton has been transferred from chlorine to nitrogen to act as Bronsted-Lowry base. A species must have at least one unshared pair of valence electrons so that it can form a covalent bond to proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached to the atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and is a base. Some examples of acid-base reaction according to Lowry-Bronsted concept is given below. HCl plus H2O will give H3O positive plus Cl negative. H2SO4 plus H2O will give H3O positive plus HSO4 negative. Similarly, H2O plus NH3 will give NH4 positive plus OH negative. It is important to note in above example water act as base with respect to HCl and H2SO4. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts as both acid as well as base is called amphoteric or amphiprotetic substance. Similarly, bicarbonate ion H3O3 negative behaves as an acid as well as a base. HCO3 negative plus NH3 will give NH4 positive, CO3 to negative. HCl plus HCO3 negative will give H2CO3 plus Cl negative. Other example of amphoteric substance is hydrogen sulfate ion conjugate acid base pair. Let us reinvestigate a reaction between acid and base. HCl plus NH3 will give NH4 positive plus Cl negative. HCl being a acid denote proton and form Cl negative ion, whereas ammonia being a base accept proton form NH4 positive ion. Now the chloride have the tendency to accept proton, whereas ammonium ion has the tendency to donate a proton. In other words, acid denote becomes a base and base accept a proton and become an acid. Thus, base formed from acid is regarded as the conjugate base of acid. So, acid formed from a base is called conjugate acid of the base. In the example above, between HCl and NH3, Cl negative is conjugate base of HCl and conjugate acid of base NH3. Acid and base, they are related by loss or gain of H positive ion, are called conjugate acid base. Thus, Cl negative and HCl, NH4 positive, NH3 are conjugate acid base pair. We can represent the acids as acid change into conjugate base plus H positive base plus H positive will give conjugate acid. It clearly indicate that acid base reaction would involve two acid and two base. These acid base are called conjugate pair. For example, acid 1 plus base 2 will give acid 2 plus base 1. A substance is capable of showing acidic character only if the other substance is capable of accepting the proton, that is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. HCl is not acid in benzene because benzene do not accept as positive from HCl. Now only neutral molecule but cations and anion may act as acid or bases. Both Arrhenius and Bronsted-Lowry concept require acid to be a source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acid. According to the Arrhenius, a base is a substance which gives OH negative ion in solution. NaOH in water give Na positive OH negative, whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, CO3 2 negative plus H positive will give HCO3 negative. Carbonate ion CO3 2 negative cannot give OH negative ion in aqueous solution. It therefore cannot be an Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius base. Limitation of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcoming of Arrhenius concept, yet it cannot answer some of the established reaction. For example, it cannot explain reaction between acidic oxides like CO2 and SO2 SO3 with the basic oxide like CaO, BO, MgO, which takes place even in the absence of water. CaO plus SO3 will give CaSO4. Clearly, in the reaction between CaO and SO3, there is no proton transfer involved in reaction. The acidic nature of compound like BF3, FeCl3, AlCl3, Lewis concept of acid in base. G.N. Lewis in 1923 proposed a more general definition of acid and base, which is based upon the donation and acceptation of electron pair. According to Lewis concept, acid is a substance which can accept a pair of electron. Base is a substance which can donate a pair of electron. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbital to accommodate one or more pair of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance which with unpaired electron can behave as Lewis base. Thus, the acid-base or neutralization reaction involves the formation of carbonate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride BaF3 and ammonia NH3 is a typical Lewis acid-base reaction. Lewis acid. According to the concept, Lewis acid may be classified as molecules having central atom with incomplete octet of electron. Boron trichloride, boron trifluoride, aluminium trichloride are base acids of this type. It is clear that central boron and aluminium atom has only 6 electrons. Simple cations. All the cations are short of electron and can behave as Lewis acid. Large size cation like Na positive, K positive, Ca2 positive, Ba2 positive, etc. behaves as weak Lewis acid. This is because these have little tendency to accept electron. On the other hand, small sized cations such as H positive, Ag positive, Li positive ion has a strong tendency to accept the electron pair and are strong Lewis acid. In addition, highly charged cations have a high tendency to accept electron pair related to the low charge cations of given metal. For example, Sn4 positive is a strongest Lewis acid than Sn2 positive. Some of the typical example of Lewis acid base reaction are Lewis acid Ag positive plus Lewis base NH3 will give AgNH3 twice positive. Cu positive plus 4 Cl negative will give CuCl4 2 negative. Molecules in which central atom have available d orbitals and may acquire more than 8 electrons. Compound such as AlCl3, SiF4, SnCl2, SbF5 and SO3 are Lewis acid where the central metal atom are expand its valential. For example, SiF4 plus 2F negative, SiF6 2 negative, SnCl4 plus 2 Cl negative will give Cl6 2 negative. SO3 plus R2O will give R2OSO3. Molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represent an interesting example of double bond between carbon and most electronegative oxygen atom. Oxygen being more electronegative has the tendency to attract the shared pair of electron more towards in CO2. As a result, it acquires positive charge on carbon atom, becomes electron deficient, that is Lewis. acid and attacks the oxygen of hydroxide ion Lewis base. Similarly, sulfur trioxide act as Lewis acid towards water. Lewis base. According to the concept, Lewis base may be classified as one of the following types of substance. Lewis acid base concept discussed above is widely used because of its simplicities in many acid and base reactions. In spite of its wide application, then Arrhenius and Bronsted-Lewis have similar disadvantages as given below. Lewis concept is too general and consider all reaction forming a coordinate bond to be a base reaction. This is, however, not true always. Next is formation of a coordination bond between acid and base is a basic of Lewis concept. However, a well-known acid like HCl, HNO3, H2SO4 do not form any coordinate bond with bases such as NaOH, KOH. Accordingly, HCl, NH3, H2SO4 should not be regarded as acid according to Lewis concept. Lewis concept do not give any uniform scale of acid and base structure. Lux flood concept of acid and base. A concept of acid and base are prepared by Lux in 1939. This concept was further explained by Flood. According to Lux fluid concept, acid is any substance which accept an oxide ion, whereas a base is a substance which gives up oxide ion. Lux fluid base can be represented as base will give acid plus O2 negative. As an example, CaO will give Ca2 positive plus O2 negative. PbO will give PbO2 positive plus O negative. More examples are given here. Solvent system concept. The solvent system concept of acid and base was postulated by Cady Easley in 1928. It is an extensive to Lorentz-Bronsted concept and it's applicable to both protonic as well as non-protonic solvent. According to the concept, an acid is a substance which either by direct dissociation or by interaction with the solvent give cationic characteristics of solvent. A base is a substance which either by direct dissociation or by interaction with the solvent give anionic characteristics of substance. The characteristic cation anion of solvent are the ion produced during the auto ionization. The prefix auto means itself. To illustrate the concept, let us consider auto ionization of some proton and non-protonic solvent. Acid plus base will give acid plus base. H2O plus H2O will give H3O positive plus OH negative. NH3 plus NH3 will get NH4 positive plus NH2 negative. SO2 plus SO2 will give SO2 positive plus SO2 negative. It is important to note that acetic acid behaves as acid in water as it produces the cationic characteristics of water. CH3COH plus H2O will give H3O positive, CH3CO negative. Acetic acid behaves as a base in sulfuric acid as it produces the anionic characteristics of solvent sulfuric acid. CH3COH plus H2SO4 will give CH3COH2 positive, HSO4 negative. Urea dissociates very readily in water and give neutral solution. However, urea dissolves in liquid ammonia and behaves as a acid because it gives the cationic characteristics of solvent ammonia. NH2CO CH2 plus NH3 will give NH4 positive plus NH2CO NH negative. Similar to Arrhenius concept, neutralization reaction may be represented as combination of cationic characteristics of solvent with the anionic characteristics of solvent to form the solvent molecule. Some of neutralization reaction in various solvents are given below, like liquid ammonia, NH4Cl plus NaNH2 will give NaCl plus 2 NH3. HCl plus CH3CONa will give NaCl plus CH3COH. SOCl2 plus Me4N twice SO3 will give 2 Me4 NCl plus 2 SO2. NOCl plus NaNO3 will give NaCl plus N2O4. It is important to note that neutralization according to solvent system concept is a reverse of Autoionization reaction. Type of solvent. Solvent can be classified in a number of way on the basis of their physical and chemical properties. Broadly, there are three ways in which solvent can be classified. Protonic, a protonic solvent. Solvents which contain hydrogen and can lose hydrogen in the form of proton are protonic. Common example are H2O, NH3, H2S, HF, etc. Solvent from which hydrogen cannot be obtained in the form of proton are aprotic solvent. Common example are NH3CN, C6H6, etc. Solvent like N2O4, SO2, HCCl4 are called aprotic solvent. Acidic and basic and amphoteric solvent which have strong tendency to give proton are acidic solvent. Example H2SO4, HFCH3COH. Basic solvent are ammonia, hydrazine, pyridine. Solvent which displays both acidic and basic properties are amphoteric solvent. Example like water, methyl alcohol. Ionizing and non-ionizing solvent which undergo self or auto-ionization are ionizing solvent. Typical example are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. Solvent which do not ionize are non-ionizable. Example benzene, carbon tetrachloride. Such solvent are non-polar and have low dielectric constant. Effect of solvent on acid strength. The strength of an acid or a base depending largely on the nature of solvent used for its dissociation. Let us consider the dissociation of hydrogen chloride in three different solvent: ammonia, water, sulfur dioxide. On one can clearly see that HOClO is a strong Bronsted acid in NH3, a weak base in water and a strong base in H2SO4. The acidity and basicity of a protic solvent plays an important role in choosing a solvent for chemical reaction. The strongest acid which is available in a protic solvent is that which result from the self-ionization of solvent. Likewise, the strong base available is that which result from the self-ionization of solvent. Let us consider, for example, the following auto-ionization reaction. 2H2O will give H3O positive plus OH negative, and H3 will give NH4 positive, NH2 negative. CH3COH will give CH3COH2 positive, CH3CO negative. In aqueous solution, the strongest acid which can exist and which can be available for reaction is the hydronium ion H3O positive. It means that all the strong acid known to the chemist appear to be exactly equal strength in aqueous solution. This results from the fact that acids such as perchloric, hydroionic, hydrobromic, nitric, and hydrochloric acid all are strong proton donor. Then is the hydronium ion. Thus, all these acids react completely with water to form hydronium ion. Example is given: HX plus H2O will give H3O positive plus X negative. So here our chapter is completed. Thank you.